My name is Matthew Zimmerman. I am one of the founders of FarSounder and the FarSounder CEO. So thank you for taking the time to hear about our 3D forward-looking sonar products and how they relate to today's USV missions. Over the past decade, we've seen the rapid development of USV capabilities and applications. Of course, USV technologies really started in well-charted locations where the operators were not concerned with unknown underwater hazards. These projects and applications were mostly focused on above-water collision avoidance and following the coal regs. Over time, these technologies evolved into operations at longer ranges, primarily in deeper water, and mostly still ignoring subsurface obstructions. Now that the core technology of USVs is really well tested, it's clear that the missions and applications for USVs are expanding into new locations. And we're starting to see applications such as force projection into high latitudes, places with ice and poor charts, security patrols in austere ports, ship-to-shore pathfinding, and of course, shallow water navigation for MCM. All of these use cases require a better understanding of what's underwater ahead of the vessel. And that's where 3D forward-looking sonar can play a role. So you might ask, why 3D forward-looking sonar? Well, it's clear that when there's no crew on board, your situational awareness is much smaller and more difficult, and this adds to a higher risk of collision. Electronic charts provide only historical data, and as many of you probably know, the vast majority of our charts are horribly outdated, and only about 25% of our world's oceans have actually been charted. In shallow coastal areas, that's only about 50% have been accurately charted. So there's huge areas of unknown shallow waters. And of course, above water sensors are limited to objects and obstacles above the water. 3D sonar is really designed to let you know what's underwater ahead of the vessel. Probably all of the USVs that you're working with already have a sonar, a basic sonar looking straight down, called an echo sounder. That won't tell you anything about that rock ahead. And your above water sensors also won't tell you anything about that rock ahead of the vessel under the water. If you take a traditional down-looking sonar and point it forward, be that an echo sounder or a 2D multibeam, you're still going to have a really hard time detecting those rocks. So to be an effective navigation tool, a forward-looking sonar must have a wide field of view and a fast update rate, and be capable of sensing from the sea surface all the way to the sea floor. And that's exactly what FarSounder's unique technology can do. Here's an example of our product's 3D sonar information. We generate a complete image ahead of the vessel to navigationally significant ranges with a single ping. The idea of this capability is really quite simple, but we've been working and developing this technology for many years, and last month we celebrated 22 years. So FarSounder, though we're new to the USV application, has been around for quite a while in the marine market. Our customers use our products to avoid a wide variety of obstacles, such as shallow sea bottoms and coral heads, icebergs when operating in polar regions, large whales, rocky pinnacles, whether they extend above the surface or not. Of course, lost shipping containers are great sonar targets when they're floating at or below the sea surface, and any other unknown obstacles such as old wooden piers and breakwaters. Our products are intended to provide the vessel with a clear picture of what's underwater ahead of the platform. And our systems generate 3D information ahead of the vessel, as well as build a map of everywhere the vessel's been. Here is a short video example of what the user interface to our products look like. These have both 3D sonar view, which we see here on the left. The operator can rotate and change the perspective, as well as a chart overlay that we see on the right. Everything inside that pie wedge is real time ahead of the vessel, and we can map the seafloor in 3 dimensions out to at least 8 times the depth of water below the sonar, whereas we can still see in-water targets out to the full range of the sonar like we see here with these bridge pilings. In addition to the real-time forward-looking capabilities, we also build what's essentially a gridded bathymetric output, a map. We call this our local history mapping. And all of this is tide corrected using Admiralty Total Tide. Of course, for USV applications, some may be happy with a remote operator display, but many more advanced USVs are operating in unmanned, autonomous, or semi-autonomous modes. For these vessels, our systems also include a standardized machine interface that allows your vessel control system to access all of the sonar information that's being produced by our products. And this machine interface is available through a standard Ethernet network. On our website, you can read more about our software development kit, which includes all the details to this machine interface. Now that you've been introduced to what our technology and products do, let's take a few moments to talk about how they do it. So I wanted to explain the difference between 2D and 3D processing. So in this example, I took a single ping from one of our sonars as we were doing testing and approaching a commercial pier. We can see this dotted line that I've overlaid on top of the left panel, which shows traditional 2D processing. In this case, colors map to signal level, where a lighter color represents a brighter, louder reflection. And we can clearly see that there is a strong reflection trend along that dotted line. But the 2D processing doesn't tell us how deep that reflection is. Is it safe and deep, or is it shallow and dangerous? On the right-hand side, I processed that same ping with our 3D sonar processing, and we can see that same horizontal information in the horizontal slices, but in the vertical slice, we can even see the seafloor separated from that pier reflection. It's clear that just looking at 3D signal information like we see here is really complicated, and that's not sufficient for an automatic vehicle control system or even a standard bridge crew to understand. Therefore, that's why we developed a further processing stage, which we call target modeling, which extracts the relevant 3D information from the 3D data. And on the right, you can now see what our standard 3D output is for that same ping. In this case, you can clearly see the pier wall coming from the sea floor up to the sea surface. However, if this was an underwater obstacle, the 2D processing would not be able to tell you if that object was deep enough to be safe or shallow enough to be dangerous. And that's why 3 dimensions are so important. I mentioned earlier that we can map the sea floor out to at least 8 times the depth of water below the sonar. If you look on our website, we have lots of videos and screenshots. Most of them are showing even more than 8 water depths, but we like to be conservative with our specifications. And I want to talk about where this limit comes from. It's really a limit of physics. With your standard down-looking sonar, all of your energy reflects off the seafloor, and pretty much all of it comes back to you. However, if you point that energy forward at a steep angle, most of it comes back, but some of it reflects forward off the seafloor. At a shallower angle, less reflects back to you and more reflects forward, until eventually you get to some angle where the seafloor is reflecting the sonar energy really well, but it's reflecting forward. You can think of the seafloor acting like a mirror and the sonar acting like a flashlight. If you're perfectly lined up with your mirror and you shine a flashlight on it, the flashlight is going to reflect back on you. But once you're off axis, reflecting from the side, the mirror is still going to reflect that light really well, just not back to you. And that's exactly what the seafloor is doing to the acoustic energy. It turns out this reflection point is about 8 times the depth below the sonar. It depends a little bit on the bottom composition. And with a rougher, harder bottom, you'll typically get more than 8 water depths, sometimes 10 or 12. However, if there is an object on the seafloor, now that reflection is going to have an edge that can reflect back to the sonar. And that's how we're able to detect in-water targets on the seafloor, even beyond our bottom mapping range. In this example here, we're looking out a little more than 8 water depths, about 10 water depths ahead of the sonar. Colors mapped to depth, where blue is deep and yellow is shallow by the color marker that we see at the bottom right. And from the green, we can see that it's about middle of that water depth scale. And in this particular data set, we can see 4 bridge pilings that correlate really well to the bridge location on the chart. Those first 2 bridge pilings are being displayed in 3 dimensions because they're within our 3D bottom mapping range. However, those 2 farther targets are being detected and displayed as in-water targets with range, bearing, and reflectivity. In this case, because they're beyond the 3D bottom mapping range, they are colored relative to the reflectivity, which is shown by the color scale at the top right of the display. Once we're into that range beyond our bottom mapping, the sound waves are reflecting off the sea floor, off the sea surface, maybe both, maybe more than once, and we don't know exactly how they are reflecting. Well, that's not exactly true. If we could measure the acoustic propagation properties of the seawater, then we can actually unwrap all of these reflections and produce that true 3D image out to the full range of the sonar. However, because we're a forward-looking sonar, it's ahead of the vessel. We haven't gotten there yet, so we can't measure those properties. Therefore, when we're operating in this domain, which is called the multipath domain, we're only giving you range, bearing, and reflectivity. But still, when you have an object on the seafloor, in the water column, or just below the sea surface that has an edge which can reflect back to the sonar, we can detect it even in that multipath domain. Here's a great example of an Argos 1000 operating at 1,000 meters range. We can see the sea floor being depicted ahead of the vessel in in greens and blues. In this example, we are mapping about 10 water depths, and we see a row of in-water targets at the full range of the sonar. This is beyond the bottom mapping range at 1,000 meters ahead, and with the chart overlay, we can clearly see that it correlates to the shoreline. Each of the Argos series sonars use a product-specific in-water sensor, which we call the transducer module. The primary difference between these units is the number of elements in their receiver arrays. More elements results in a higher resolution sensor capable of operating out to longer ranges. The Argos 350, shown at the left at the bottom, has a receiver array with about 50 receiver elements. The Argos 500 has about 100 receiver elements, and the Argos 1000 has approximately 200 elements. All of these models utilize the same sophisticated sonar processing, display software, and machine interface, and all have the same type of inboard equipment, which we call the power module. A FarSounder supplied cable is used to connect the transducer module to the power module and features an underwater wet mateable connector. This allows the transducer module to be installed or removed by a diver underwater. The primary difference between our 3 models is their maximum operating range, and they're cleverly named Argos 350, Argos 500, and Argos 1000 for their maximum detection ranges of 350 meters, 500 meters, and 1,000 meters respectively. So that's from over 1,000 feet ahead with the Argos 350 to over a half a nautical mile with the Argos 1000. Of course, they also have slightly different fields of views when operating at different ranges and different vessel maximum speeds. Aside from the forward-looking 3D capabilities of our products, we have a few other innovative features that I wanted to touch on briefly. The first, I mentioned a little bit before, is our local history mapping. Although we focus on being a real-time, forward-looking sensor, we are collecting a whole ton of depth measurements as the vessel travels. So we didn't want to just throw them away. Instead, we've collected all of those depth measurements, gridded them into a bathymetric map, essentially, which we call our local history mapping. We do this in real time with no user interface. There's no manual scrubbing or cleaning. So it's not quite as sophisticated as a full-fledged survey tool like something from QPS. By the way, we do integrate directly into the QPS ecosystem through their software if you do want to use FarSounder sonars in a formal survey. However, our local history mapping capabilities is really interesting for when a vessel comes back to an area they've been previously. They can now have some sort of an idea of what to expect ahead. And if it's changed since the last time they were there, well, the forward-looking sonar will show the differences. It can also be used for performing informal surveys like an anchor survey before dropping the hook. Right now, all of this data lives on board the FarSounder computer, and it's corrected for tide changes using Admiralty Total Tide. However, we are working actively on a pilot program to actually share this sonar data across the FarSounder fleet. We'll be launching this pilot program in the fall and expect to have the capabilities available for all FarSounder customers near the end of Q1 next year. So we're going to be taking this local history map off of the vessel and sharing it across the fleet. Of course, this will be opt-in. There's no requirement to actually share this data publicly across the entire fleet. Aside from our local history map, we also have some other overlays on top of our chart display, one of which is AIS. That lets the operators quickly correlate what are these sonar targets. If it's something on the chart, it's a fixed reflection and a fixed obstacle. But it could be something transient, like a passing vessel. And passing vessels make wakes. Wakes are made up of bubbles, and bubbles are great sonar targets. So when you see a row of sonar targets that correlate with an AIS track, you can have high confidence that those are actually the bubbles from that passing vessel's wake. And the AIS overlay allows the operator to quickly make this correlation. This same correlation can be used automatically by the vessel's control system when it does its own data fusion between the different sensors it has on board. Similar to the AIS overlays, we also offer ARPA overlay on top of our charts. Our software includes display of standard S57, S63 format charts with the sonar overlay, the AIS overlay, and the ARPA overlays. We're not trying to recreate the full ECDIS experience. We're not doing voyage planning and route management. We are focused on how to make the forward-looking sonar and the local history maps information really easy to understand quickly and comfortably for both standard bridge crew and, in the case of USVs, for their automated and remote systems. Everything that I've talked about so far is what lives on board the vessel as part of our standard products. But besides our local history mapping capabilities, we also have an opt-in program, which we call our Expedition Source Ocean Data Collection Program. This is for select customers who are traveling to exotic locations and really want to contribute to science, and also want to participate in making the systems better. As part of this program, we send participants a USB hard drives, which they plug into their FarSounder computer, and it records all the raw data as they're underway. Here's a map of some of the places our customers have recorded data. To date, we have over 60 terabyte of sonar data that's been collected, and we have about 85 terabytes of drives still in the field. These are data collected from different sonars in different locations, different times, and different conditions. All of that information helps our engineering team when we're trying to improve and expand our algorithms. Additionally, with user permission, we've been submitting a subset of this data to the IHO as part of their crowdsourced bathymetry efforts. I'm part of the IHO's crowdsourced bathymetry working group, which is a working group which operates under the IHO, figuring out how to take advantage of all of the possible information that could be contributed by the thousands and thousands and thousands of vessels operating on our waters every day. All the data that we submit to the IHO program is also shared with Seabed 2030, which is a global initiative to map the world's oceans. To date, we've collected just under 25% of the world's oceans in a full global map. Clearly, there's a lot of work to be done, and crowdsourcing is one of the methods that can help get us there. So any data that we submit to the IHO also goes into Seabed 2030, and that data is available for anyone to use globally at no charge. So why is this exciting? Well, in one example, the Canadian Hydrographic Service is working on generating new updated charts for the High North. And these are areas where they don't have any official survey data. In one particular chart, chart 7053, they were able to include data collected by a FarSounder customer and submitted to the IHO through this program. Because FarSounder's customers have high-quality metadata, the Canadian Hydrographic Service was actually able to calculate the total error and found that it was within their error budget. Therefore, they're able to include that information, this crowdsourced information, into one of their official charts. This is a really exciting progress and something that I expect to see more and more hydrographic organizations taking advantage of. Argos sonars are in use today in a variety of applications and marine market sectors. Of course, today we're talking about USVs, but we've been installing our systems on Navy vessels, Coast Guards, yachts, cruise ships, research vessels, vessels going from the Arctic to the Antarctic and everywhere in between. Basically, if you care about what's underwater ahead of the vessel for your application and your mission, FarSounder is a great match for those requirements. Every vessel is unique, but our installation concept is essentially the same. In most cases, our customers are using a fixed installation. In these cases, we have them build a fairing, which is essentially a tube that is integrated into the hull, and the sonar is installed from the exterior into that fairing tube. This approach utilizes no moving parts and is fairly easy to construct. Here are a couple of examples with the sonar fairing integrated onto the center line of a raked bow. The vessel on the left was a refit for a Dutch Navy vessel, and the vessel on the right was a new build. Both of these examples show the sonar fairing being installed on the center line. Of course, there's a bulb that's also a great location for the installation, and the system can even be installed offset off to the side of the stem. Of course, for some users, a hoist installation is preferred, and those are sort of cases where there's a special need for deploying the sonar. In this picture here, we show the hoist that was used on the Sir David Attenborough, the research vessel from the British Arctic Survey. This vessel is a full-fledged icebreaker, and when breaking thick ice, the sonar is retracted and protected from the ice by the sonar blister. And when the vessel's operating underway, they can deploy the sonar and use it for its forward-looking capabilities. However, the sonar doesn't always need to be installed on a hoist, and here's an example of the Argos 350 that was installed on a composite refit of about a 23-meter hull. In this case, the fairing was glassed into the existing hull, and the transducer fills that opening in the front. The Argos 350 we found to be very popular with a number of mid-size USVs, and many of them are utilizing a hoist mechanism developed by one of our partners, C4R Marine Solutions. Their hoist is designed specifically for the Argos 350, and the Argos 350 can be supplied with its connector on top, making and facilitating the hoist installation really easily. One of the advantages of the C4R solution is when the hoist is retracted, it can be perfectly flush with the hull. For smaller, high-speed USVs, this might be a preferred solution. If you want to learn more about all of our installation options, take a look at our website. We have lots of example pictures, installation drawing packages, and design guides are available for download. And of course, reach out to us. We're happy to assist in your installation design at no charge. Additionally, if you want to dig into the details of all the technical things about our products, you can check out our free online training at training.farsounder.com. We offer both end user training classes and technician training classes. In addition to the training, which we offer to all of our customers, we also offer our customers regular software updates. And of course, we can support them also through remote TeamViewer sessions. At the end of the day, the operations for USVs are really very similar to commercial users, and it's driven by the need to access places safely, whether that's operating in shallow waters, in poorly charted areas, avoiding unknown obstacles like ice, rocks, and corals. And really, this all translates down to reducing mission risk and increasing the ROI for your vehicles. So thank you for your time. I appreciate you spending your time with me today to learn about 3D forward-looking sonar for USVs. Once again, my name is Matthew Zimmerman. I am the CEO at FarSounder, and I'd be happy to answer any questions that you may have.